I want to take a brief look here at the Nernst equation. Now the Nernst equation, as the top here, is given on the AP exam in the formula section, and it looks a little scary, but what it really does for us is if we have an electrochemical cell, everything here is done under standard conditions. So when we figure out the voltage, okay, then we are figuring out the standard voltage if everything is 1 molar. Now, what if it's not 1 molar? That's where the Nernst equation is going to come in. Now we can go back, we were doing a worksheet where we're looking at a cell made out of silver and lead, and we decided that the lead equation, since it's smaller, it would have to be turned around, and we got this equation here, so silver plus lead metal turns into silver metal and lead ions. And we actually figured out here that the E0 value for this cell would be 0.93 volts. And that'll be a positive value. We're going to need that information in a moment. Now, looking at the equation itself, what's written in the AP test is a little scary looking because of the way it's set up, but it's really two equations. So you could say the cell voltage, now the fact that it has a little zero here, okay, what that means is that's a standard cell, everybody's 1 molar, and if we have one here with no little zero, that's just a non-standard cell, where things don't have to be 1 molar. Then we have this big expression here, which is just going to be used to kind of adjust the voltage according to the different concentrations. So we have several values in here, and we have R. Now R is the ideal gas constant, and it keeps showing up in a lot of different equations, and in this one we want to use this last value, the one with volts, which makes sense, 8.31. Now notice that's the same one as if we were doing joules, and it's also the same one if we were doing kilopascals, as our pressure. So we keep seeing that same number over and over and over, but that's okay. Temperature here, that's just temperature in Kelvin. Okay, N is the number of electrons that we deleted, so when we put the two half reactions together, and so for this equation that we're doing, it actually came out to be N equals 2. And the last one here is the Faraday constant, and that's given on the exam as well. Now the last part here is Q, and we'll come back to that in a few moments. Now on the other side, we have an equation, and it's really the same equation. So if we took this part, E of a cell equals the standard cell, and since R is a constant, and if we're working at 25 degrees, then we could put in 298 Kelvin, and that would be constant. Faraday is a constant, and log base 10 versus log, E, a natural log, we could make that change, and there's a number involved in there. So if we made all those little number changes, they would come in to be 0.0592 over N. So N is the only little piece of that we need to keep. So this is actually the equation that I use a lot, and that is that the non-standard cell's voltage is the standard cell voltage minus 0.0592 over N log of Q. Okay, back to our equation. We said that if, so we're going to use this piece right here, equals all of this. And if it doesn't say the temperature, they usually mean 25 degrees Celsius, 298 Kelvin. So the one little piece of this we haven't done yet is Q. Now we've seen Q a long time ago when we were working with equilibria, and if we wanted to, remember that's our test quotient, and if we just look at our equation, then we say, okay, Q is the exact same expression as K, and all we have to do is say it's the lead ion concentration divided by the silver ion concentration squared, because of the fact that this has a 2 in front of it. So the difference between this and a K is in K we'd have to put in equilibrium values. For Q we put in any values we happen to have. So if we have a new cell where the silver is 0.5 molar and the lead is 2 molar, let's put that in and see what we get. So lead is 2 molar divided by silver, which is 0.5 molar, squared. And we can see what happens if we divide by 0.5. That's the same thing as multiplying by 2. So this would be 2 times 2, and again 2 times 2 times 2. So this should come out to be about 8. Now we're going to go ahead. Remember that n is equal to 2. And all we have to do is work out our whole cell. We know that the E of the cell was positive 0.93 volts. And let me see if I can write all this out without making too big of a mess. So the E of the cell, of the non-standard cell, is equal to 0.93 volts minus 0.0592 divided by 2. That came from our balanced equation. Log of 8. Now I'm going to go grab my calculator and calculate this. For log of 8, I get 0.903089, that kind of a number. And when I multiply by 0.0592 divided by 2, I get this whole section being 0.0267. So my answer is 0.93 volts minus 0.0267, and that comes out to be about, well, not about, 0.903 volts. And I could probably round that up to 0.90. Now we were saying before that if we reduced the silver ion concentration, that would kind of drive the reaction back. And if I increased the lead ion concentration, that would also drive the reaction to the left. So both of those would be expected to lower the voltage. And instead of being 0.93 volts, we see we get 0.90 volts, and it really has lowered the voltage. So that's how we use the Nernst equation.